let's see. So in the last class, we got started with the topics in the course which have to do a little bit with transport that has some flavor of, especially the superconductivity is a flavor of a many particle or a many body correlated transport. In addition to that, we'll see that these are the two phenomena we are going to kind of cover for the remaining part of the course: superconductivity and topological insulators and such materials. They exhibit some aspects of transport that are incredibly precise. The precision of some of the transport parameters that we will come across in superconductors and things analogous to the topological insulators which happen in semiconductors, like the integer quantum Hall effect. There are some transport parameters in them, such as conductance, or here we'll see frequency of oscillations is so precise that now they have been turned around to define what do we mean by voltage and resistance and such things. They are used as parameters. Transport, you might imagine, is a very we have talked a lot about scattering, so it's a disordered system, and there is no way one would imagine that if I take two chunks of materials, they're clearly the defect densities, everything is different in them, they're located randomly, so there's no way one could imagine that some transport parameter that samples all particles that are moving, which are 10 to the power 20 particles moving inside a solid, could still show incredible precision and independence on how exactly you prepared the sample and such things. So that's very amazing. And whenever such precision shows up, we are increasingly realizing that that has to do with some sort of topological or geometric protection rather than something that depends on details. But so we'll see that first today and for the rest of the course as well. And many of these things it would be really nice to have in sort of room temperature semiconductors, and we'll see that semiconductors, especially in the form of two-dimensional electron gas, led to for example, the discovery of integer quantum Hall effect and such things. And we'll see how they're slowly being recognized as things that are very desirable for future generations of even electronics or photonics and such things. So it's kind of the concepts and the ideas, if we can recognize them, we can build them into some things that can do useful, useful functions for us. Okay, so what we discussed in the last class was somewhat of a freewheeling way of looking at how superconductivity first was discovered by the vanishing of the resistance, and then we talked a little bit about if I form rings, then I can have currents flowing in these rings essentially forever, as long as they're superconducting. And we also saw that the electronic specific heat of a superconductor showed behavior which was indicative of the presence of a gap, energy gap, meaning instead of being linear with temperature, the electronic specific heat is generally linear with temperature. But if you measure a superconductor below the critical temperature, the specific heat shows an activated behavior, and from there you can calculate that there must be some delta or energy gap associated with it. And this is a hint towards a microscopic nature of superconductivity, which we are going to talk about today as well. So, and then we talked about one of the reasons why, even though some of the pioneers of quantum, who developed quantum mechanics, Niels Bohr, even Einstein, and many people tried very hard to solve and explain superconductivity, but a lot of it had to wait till another experimental discovery, roughly 20 years after the discovery of the vanishing of the resistance itself, which is the Meissner effect, right? Which is the expulsion of the magnetic field. We talked a little bit about that. And right after that, the London brothers, so they're two brothers, last name London, they gave what is kind of a semi-classical theory of the Meissner effect. And they didn't appeal to the fact that they didn't talk about the microscopic picture, but they explained how one might be able to get such a behavior. And the crux of their theory was that all the particles that are contributing to currents inside this material must move in unison as one body, not as independent objects, but as one, collective object. So some as if they are bonded together, so they form coherent object. So they spin in some sense. Okay, instead of single electrons going around, the whole thing spinning. You can think of it that way. So that was essentially also they calculated something we also evaluated in the last class, which is the London penetration depth. How deep into a superconductor does a magnetic field penetrate. And so it took quite a few years after that for Landau and Ginzburg to give a theory of superconductivity, which I'll talk a little bit about today. But the main idea, I think we kind of talked about in the last class, and using this main idea we are able to explain all the hallmarks of superconductivity, is that these materials exhibit, or the electrons in this material follow a wave function, which we wrote as, there was nothing very surprising at the face of it, writing a wave function as an amplitude and a phase, right? But the big catch here was that this wave function is not a wave function of one electron. It's the wave function of all the electrons. It's a many particle wave function. Does that, that was the main thing that we kind of said, that this is, and this came about really from both from a macroscopic picture or a thermodynamic picture from Landau and Ginzburg, and then it was made much more microscopic by Bardeen, Cooper, and Schreifer later on. So we want to track a little bit of that. But I want to kind of just highlight, what Landau and Ginzburg had proposed, that without too much of a microscopic insight as to why it might happen, by looking at all the physical phenomena, what they realize is, if I have a macroscopic wave function, I can explain all the physical phenomena. That was the idea, their idea. And by using this and applying our right away what we could, so there are really the three hallmarks, if you might, of superconductivity are, the vanishing of the resistance, right? And then the Meissner effect, which is expulsion of the magnetic field. And the third one, which let me just write them down. So resistivity is 0. Actually, I shouldn't say goes to 0. It is exactly equal to 0, right? So, and that's something we discussed in some length last time. What does that mean? It means, for example, a supercurrent would go forever. It's not going to decay at all because the resistance is exactly 0. And the second was the effect. And the third is what one would call as a flux quantization. And I was trying to get to this towards the end of the last class, but I think I didn't quite finish it. So I'll just do a quick run through of, again, showing that if I assume a macroscopic wave function like this, then I can explain all the three properties or the hallmarks of a superconductor. So another way to just think about this is because mod psi squared in traditional quantum mechanics is the probability density of finding a particle at some point r, right? Here it's macroscopic though, right? So if I take mod psi squared, what should I get here? I should get the total number of particles, or the density, if you might, right? This is not a probability anymore. It is actually the number density per centimeter cube of particles. So as a result, I can, because mod psi squared is equal to the number density of the superconducting particles that are in there per centimeter cube, you can write this wave function also as a square root of the carrier density times e to the power I theta of r, right? So that's the reason why you can write it like that. And we initially have assumed that let's look at situations where the carrier density is uniform everywhere. So we've looked at those situations. So under that approximation, the wave function is just square root of a carrier density times e to the power, a phase. And this phase is, again, just to be very clear, the phase is just one phase for the 10 to the power 22 particles here. And that's also rather incredible that one can that matter will behave in this manner, that all such a large number of particles will combine together to give one phase. So this is something it's a bit of an approximation where the carrier density is not changing, but I think using this, we're able to explain all three rather easily. If you take the space dependence into account, you can still explain them. It needs a little more work, So, yeah. So the idea here was that we have also seen in all our analysis earlier that the total current is for any quantum mechanical situation for which the wave function, be it one particle or be it many particle, the total current is given from the wave functions. So if I okay, I'm going to write E here, but just to be clear, I should write E star because we'll see later it's a Cooper pair. It has charge of 2E rather than 1E. But that's the understanding, is the charge of the particle carrying the currents and all that. So we know that it looks like this, right? Wave function psi, and then we use minus I h bar gradient, right? Minus psi, the inverse of that, right? Right. So we saw that this was with the situation if there is no magnetic field, but the moment you introduce a magnetic field, there is another term here which looks like this, psi star psi by the mass times the vector potential, magnetic vector potential. Right? So we wrote that in the last class, and you can derive this from the prescription that in the presence of a magnetic field, the momentum operator becomes minus IH bar gradient. In the absence of a magnetic field, this is the momentum operator. But in the presence, it has an extra kick from the magnetic field term, and that's the term, right? So once you introduce this into the current expression, you will get this term come out from, split off. Okay. And so using this macroscopic wave function or many body wave function and plugging it into all left and right, both the terms here, what we wrote down was that the current was given by the charge times mod. So I'll skip the size. I'll write it in terms of the carrier density, E times the carrier density, and times h bar times the gradient in real space of the phase. Right? H bar times gradient of the phase. I'll also pull out the mass here, okay? Plus the charge of the particles vector potential. So that's your total expression for the current, or the superconducting current. This is the expression, and it depends on the phase and phase gradients, and it depends on the magnetic field vector potential in the form of the vector potential. In some, just to be also, if it causes some confusion here, I have assumed in books you will also see it is given as minus EA, but here our, just a sign convention, unfortunately, our E here just is plus 1.6 times 10 to the minus 19 coulombs, but in Cooper pair it's 2 times that. But essentially, don't bother too much about it. There's a minus or plus. We are using plus from a sign convention perspective. But that's the basic idea. And the fact that you can recognize right away that this quantity out here from our analysis of traditional transport, current is charge times carrier density times the velocity. So this is an effective velocity, everything sitting here, which depends on two quantities. One is the magnetic field, the other is the gradient of the phase, spatial changes in the phase, macroscopic phase of the wave function. And from here, if I look at the situation where I if I take a piece of superconductor, okay, let's take a cylinder like that, and I apply a magnetic field to it, and from this analysis, what experimentally we see is deep inside the superconductor there is no magnetic field; it has been expelled, right? Inside the superconductor, there is no magnetic field, so essentially, what we see from here is that. All right, I'll just. So the magnetic field lines will go around the superconductor, and there'll be a certain depth to which they will go. Very thin depth, and into which they'll go, and there'll be a current that will flow all around the surface of the cylinder, actually the other way, I guess, so that it inside the superconductor they're all cancelled exactly. Does that make sense? So there's a circulating current outside, and inside it's exactly cancelled. So the vector potential deep inside the superconductor goes to 0. And so essentially, well, let's put it this way. Deep inside the material, there are no currents flowing either. So this whole thing is 0. Okay? Right? The current deep inside the body of the superconductor is 0. I don't want to kind of derive this, but if you look back in the last class, from here we derived the fact that there must be a London depth and all that sort of thing. We derived that from this argument. So I don't want to redo it. But I wanted to just show, there were some questions also in the last class about this discussion of flux quantization. I just want to show that. So instead of a object like that, which is a object with which has a certain topological property, which we will come to again later, this object has no holes in it. That's the topological property, and the number of holes, physical holes you put inside it, changes its topology. And let's put one hole inside this, and so we will form a concentric cylinder now, right? And so now the superconductor is a ring, okay, and inside it is a physical air, a vacuum in between, and now what happens is so in this situation, we get experimentally what is measured is that the flux inside here, the total magnetic flux here, which is integral of B dot the area of this hole, right? The total flux is quantized. It's quantized in units of it's an integer times phi naught, and this phi naught is Planck's constant by 2 times the electron charge, h by 2e, Planck's constant by twice electron charge. It's quantized, so it can be 0, 1, 2, 3, 4, and so on. Nothing in between, and this has been incredibly measured with incredible experimental precision, very, very precise measurements. And that also you can get in 2 lines from here by looking at this expression now. What you can do is sit somewhere again deep inside, away from the London penetration depth, somewhere deep inside the bulk of the material, and then choose a loop that goes all around. Okay. And let's say that loop, the path length is given by dl, where L is the differential length along the loop circumference of a material that's inside the superconductor, not inside the opening, but inside the superconductor. And inside that, what you can evaluate is what is your j dot dl. And I know you know that deep inside j is 0 inside, because you are far away from the London penetration depths. And therefore, forget about these details. You know, an integral of this, a closed loop integral of all this stuff, dot dl must be equal to 0. That much, you know, because the current is 0, right? So at every point it's 0, so you're summing 0 over the entire length. And from here, what you can write, therefore, is that, again, I think the sign convention, it's a little unfortunate here, but that's all right. E a dot dl, there'll be a minus sign here, but that doesn't matter really, times h bar times integral of closed loop gradient of the phase. dl must be equal to that, right, from this argument itself. And I think you also know that the gradient of theta is essentially d by dl, right? We're moving along. You can think of dl as a certain radius times the angle d phi, right? As you go around this certain angle phi, so times unit vector along the, you know, radius of the of that circle. And so essentially what you get here is you are just integrating d theta, really. It's an exact differential. That's what it means by that, right? So, okay, so and it's a closed loop, and when you have a closed loop like this, and just pay a little attention to this, because this will show up again later on. We talk Berry phase, quantum Hall effect, all, because this is a topological. Most of the topological properties we'll talk about is tied to what we are talking here. Pretty much all of them, actually, in some way or the other. So here the argument is very simple, that when I take a phase, the wave function is it's a single valued wave function, meaning if I start here and I go around a circle and I come back to the same point, the wave function shouldn't change its value. Does it make sense? So this is an important point here. If I go around in real space, here our parameter is the real space. I go around and I come back, it's a single valued wave function. How can I ensure that? This is fixed. I don't have to worry about this at this point. My carrier density is not changing. Therefore, the theta, when I go around 2 pi times big R, right, I must come back to what I was initially, or I can still maintain the same wave function as long as I am plus 2n times some integer times 2 pi. Still okay, right? And this little twist is what, for example, here immediately leads to flux quantization, because what it's saying here is this integral here is equal to h bar times 2n pi, right? It's not 0. It's equal to h bar times 2n pi. 0 is one of the values, one of the possibilities, but it's not the only possibility, right? So that's the important point here. And on the right side, you have a dot dl, and I think you have done enough, electromagnetism. Hopefully, this is you apply Stokes theorem here, and instead of integrating a around a loop, a dot dl, you can convert an integral around a closed loop like that to a surface integral, right? And when you go surface, you have to take the curl. How much is it curling around? This vector field is curling around. Curl of a dot ds now. You convert it into a surface integral, and this surface is essentially the area of the surface enclosed by the closed loop here. Right? That's the meaning of it. And we all know that curl of a is the magnetic field. Okay. So what we get here is minus e and b dot ds around this loop. And you can see that since there are no magnetic fields inside the bulk of the material, the only area we are worried about is the area of this hole, right? And so that clearly is minus e times the flux that is going through this hole, b dot ds, right? And on the left side, you end up with this quantity here, and you can see right away from here that you get that the total flux that can go through this hole now is h bar. 2 pi h bar is h, right? I think I'm Okay, let me just write h by e here times an integer, or n times. Yeah, I think I kind of should have chosen 2e from the beginning, but so h over e, but actually the particles here are Cooper. So whatever be the charge, this will be the situation here. It just happens to be a Cooper pair, and when you experimentally do it, you don't observe h by electron charge, but h by 2e. That's what you observe. Just wanted to fix that here. And so you can see that this quantity, therefore, is called the flux quantum, phi naught, and the total flux that will go through is that. And we'll see repeatedly that the flux quantum here will play a very similar role to the conductance quantum we have seen earlier, which is 2e squared by h. And they look similar to a little bit. And there will be some aspects to it that are similar here. Each mode, remember in ballistic transport, each mode of a conductor, be it a metal or a semiconductor, whatever you have a band states, each mode, when it's doing ballistic transport, it carries a maximum conductance of 2e squared by h. That's the idea there, or e squared by h per spin, per spin channel. And here, flux will have some similar connotation, the flux quantum, and things will happen in discrete amounts of the flux quantum. So, okay. All right, so another very important experiment before we talk a little bit more about the microscopic details and Landau-Ginzburg. Let me just go over to that experiment. Is this experiment done by Ever from GE Labs, not too far from here, not too far in space, but back in time. 1960s, and he was awarded a Nobel Prize for this experiment. It's a very beautiful experiment. What he did was, I'll describe two experiments, and I'm kind of talking about all the transport phenomena we can, because pretty much all of them you can explain with some notions of what Landau-Ginzburg have introduced, and this macroscopic wave function. You can explain all of these, and the two experiments I'm going to describe now. One of them is G.I. Evers' experiment, which is tunneling between a metal and a superconductor through an insulator. You have talked about metal and semiconductor earlier. This is now a metal and a superconductor junction. Just to be clear, metal, obviously many metals, when you cool them enough, they become superconductors. So here we are saying that this is a normal metal phase, this is a superconducting phase. This has reached superconductivity, this has not reached superconductivity. That's what we mean by a metal superconductor tunneling junction. And or sometimes in many books or papers, you will see this as written as N, which stands for a normal metal, normal, N, normal metal superconductor. And in between them, we have a large gap insulator, maybe aluminum oxide or silicon dioxide or some other oxide material, could be other nitrides, whichever way you look at it. But here's the situation. And when he, at that time, if you read his paper, what you'll see is the big challenge was how do you form a very thin tunneling gap. It was very difficult to make it, and so you would deposit these materials in vacuum. As an example here, he's looking at one of the metals is aluminum, the other is lead, and the aluminum has been very careful. This is done in vacuum, the deposition done in vacuum, but it's very carefully exposed to some oxygens that it oxidizes over about a nanometer or so of aluminum oxide. So the insulator thickness is roughly about a nanometer here. And then there's aluminum lead. They have different critical temperatures, and then he is looking at the voltage applied and the current that flows, I versus V. We have plotted IV for many situations, diodes, transistors. Now this is a normal metal and a superconductor junction. And what experimentally is observed is that if you look at I versus V, if you are above the critical temperature, and this is a tunnel junction, then your IV looks very standard ohmic, nothing very fancy. If you are above the critical temperature so it's normal metal tunnel junction. It looks like a Ohm's law picture. But as you cool this down and you go below the TC of the superconductor, then what happens is so essentially there will be a little curve feature, and then it will come back to this line again. Right? You cool it even further, go even further below TC, and make it very, very cold. At some point, it will become something like this. So as T decreases at very, very low temperatures, it becomes something like this. And similarly, it's symmetric around here, so it looks something like that. So I think, well, and then what he was able to recognize is this is actually the gap of the superconductor. In measuring the gap of a superconductor, it is this tunneling gap we alluded to earlier from specific heat and such things earlier. And the picture of this is the following. In fact, to explain this, you don't even need this many-body wave function. We can explain it in a much simpler way. So in terms of density of states, you can think of the normal metal is filled up in energy. It's filled up, the electrons are filled up till a certain Fermi level, right, in a normal metal. And if on the right side, you also have a normal metal, it will also fill up to a certain Fermi level at 0 voltage between the two. There'll be some external charge transfer, and they will equilibrate. It'll be something like this. And then when you apply a voltage, let's say I apply a positive voltage here on the right side, then I'll pull this down a little bit, okay, and then I'll be able to tunnel some electrons across. This you can evaluate easily from WKB picture or anything like that, right? And if so I'll have some current that is proportional to the tunneling WKB times, this is the slice of electrons that can tunnel through. They'll have some different tunneling probabilities depending upon the energies, but when you sum them all over, you get a straight line, right? Be it positive voltage or negative voltage. If you go up here, on the other hand, you can see you can tunnel this way now, right? So you can explain the linear ohmic behavior, and this is a standard. In fact, if we make ohmic contacts in good semiconductor devices, we use this trick all the time. Instead of a metal here, for example, this may be a heavily doped semiconductor, for example, with a gap, and these are all the electrons, so you get an ohmic contact in that way. It's not what we are trying to get to here. But now, when you go below TC, for the superconductor side, what he was able to recognize is that instead, basically at the surface or the highest energy levels, what you must have then is there's a formation of a gap, and now if you want to tunnel into and the gap energy is delta. Now if you want to tunnel, this much is forbidden. You can't put electrons in there, but if you go above or below, it's possible to get carriers in and out. So the current stops flowing till you reach that gap energy, and then you start flowing again, right? But very importantly, the gap is also changing with temperature. This is a very important observation from him, that the delta here is a function of temperature, and you can use this experiment and plot the gap as a function of temperature, and you'll see that the gap will go something like this, and this is critical temperature. Use this to measure the gap directly. And a very simple way to explain this, you now hopefully are a little comfortable with things like Fermi golden rule. You can write down the current very easily. So what we can do is think of electrons or particles going from here to there, and you say, I think you did this in the third assignment. So what is the rate at which particles may go from region 1 to region 2, right? And whatever be the nature of particles, single particle, many particle, doesn't matter. You can apply 2 pi over h bar and a certain matrix element that says I'm going from some state k in 1 to some state, say k, or state k1 to state k2 here, on the right side. And k's are just labels of the orbitals you're going into. Okay, so k1 to k2 and mod squared, and you get a Dirac delta of ek1 minus ek2, right? And I left a little space because I also want to build into it right now that this state should be occupied and that should be empty. So you can write it as a Fermi-Dirac distribution here of k1 and 1 minus Fermi-Dirac of k2. Just to be clear, we'll hopefully discuss sometime later, that this is the occupation function, doesn't have to be Fermi-Dirac. In fact, for Cooper pairs, it is not Fermi-Dirac distribution. And similarly, the rate of backward 2 to 1, from here to there, right to left, is just the reverse process, right? Except that the matrix element, I think you know by now, you're mod squaring it, it doesn't change. Matrix element mod square, be it K2 to K1 or K1 to K2, it's the same. Only things that change are the occupation functions, 1 minus f of K1 times Dirac delta of K1 minus E of K2, right? And the total current, what is current really? It is charge, dq by dt, if you might, right? Rate of change of charge. And what is, so I can write it, here is the rate, and it's the difference between current going to the right and current going to the left. So I can write it, multiply it by the charge, let's call it the electron charge here, and we get 2 pi e over h bar, 2 pi e over h bar, m of k prime. Again, I'm doing this somewhat qualitatively, primarily because I want to get to a main result. And you can see that the products will cancel again. I think you have seen that before also in Boltzmann transport. What survives is the difference of the occupation functions on the two sides, obviously, because that's what will allow for such things. And then what you end up getting here is let me just write it this way, plus Q times V. So one of the voltages, one of the sides, the potential is shifted by voltage, by the voltage. And this you must sum over all k's and all k primes to get the total current, because these are all possible transitions. And this is the golden rule way of writing current. Current is charge, rate of change of charge, and this is really one way to think about it. And this is a very general relation. And with this, when you sum over k's, it converts into an expression that I'll just write here, 2e over the Planck's constant times. Let's assume that the matrix element, again, these are very crude approximations at this point, is not changing much as you change from k to k prime. They're of the same order. And what you end up getting here is integral of dE times density of states of the first material times the density of states of second material plus QV. This is a very nice result, and you're integrating 0 to QV. That the current will be equal to that. Again, I didn't try to derive it in all its steps, but I can show that in a couple of steps here. All right. So, yeah, and here we are making some assumptions on Fermi functions. That Fermi functions, the difference of two Fermi functions is equal to 1 between the two Fermi levels. Does that make sense? F0. Or the difference of occupation functions is 1 between 0 and QV. That's what we have assumed here in this. And from here, if you look at this and you take di by dV, which is the conductance or differential conductance, di by dV, what you get, and this is what I'm after, you get some constants here which are related to some matrix elements, Planck's constant, etc., etc. But most importantly, you get the product of the two density of states on the two sides. Right. The product of the density of states of the two sides of the tunnel junction. And this is an extremely important tool, because you can see right away that if you know the density of states of one of them, you can use this to measure the density of states of the other. By changing the voltage, you can scan through. And this is the principle of things like scanning tunneling microscopy and all that, STM, where you use tunneling current and you say that I know one of the density of states. Or if you have a normal metal, the density of states is not really changing much near the surface. It's really very flat near the Fermi energy. It's not like a quantum dot. You have a very large variation of Dirac delta. But normal metal, it's almost not changing. So you can map out the density of states of the other material. So you take a STM tip with a metal, and you, for example, map out the band gap of a semiconductor, because that has the density of states picture using that. So so this is what Ever is really doing here. He's measuring the IV. Here's the IV, and here's the differential conductance, di by dV. And so of course, if you get a curve like this, and you take di by dV, you will get very small values, and then you'll get a peak here, and then it will decay, right? And that's what you're getting di by dV here. So what he's imaging is the density of states of the superconductor. This is the DOS of the superconductor, and what it's really showing is you have a gap. So the superconducting DOS looks, something like this here. Okay. And just to be very clear, if I were to zoom out and see where am I in the grand scheme of things, here this is kind of right around the Fermi energy of the superconductor before it became a superconductor. And in other words, let me sketch this out here. This is not quite good. So a metal, before it became a superconductor, had a density of states that looked something like this, or density of states, let's say. And here's the formula energy of it. Okay? And all these states were filled. Right? But when you went below superconducting transition temperature, what happened was a thin slice around the Fermi energy, which is here, meaning my energy 0 is somewhere out here, and there. I'm just sketching this roughly. They're kind of filled like that. Okay? And we're looking at things that are happening right at the Fermi surface, the surface of the Fermi. Yeah. And this is typical KT is, T is about few Kelvin, say 10 K. So this is very small, like milli-electron volt roughly. So what has happened here is the density of states, instead of being just like this, this would be the typical density in occupied states and unoccupied states of the Fermi level. It has been changed because of the superconducting transition into a very interesting way. It has become something like this, okay, and then there's a gap here. So, and that's what is being measured right there, and this is the superconducting gap, delta. And as you change the temperature, this gap will close, and finally it will become a normal metal again. So this is a temperature-dependent gap opening. That is directly measurable using tunneling transport. Okay. So, and this happened a few years after the BCS theory, microscopic theory, which kind of showed what should the gap be. And it incredibly, it's very accurate in the measurement, meaning the gaps that are predicted from the microscopic theory, it comes really close to what is experimentally measured for a wide range of superconductors, superconducting metals. There are a few which don't quite fall in this category, but most of them. Okay, so that's the first experiment. This did not even require, I just described to you, it's almost single particle, but if you look at it carefully, John Bardeen redid this picture for superconductors, but it stays the same. I mean, nothing changes here. The idea is really that the conductance is proportional to the product of DOS of the two sides. And I think you should probably, it makes sense as well, right? I mean, if there's no DOS on any side at a particular voltage, there's no current, right? So, okay, so, and I think you would also recognize that this matrix element square will have all your WKB sort of, K, K times L and all that, all the decay functions and all that, that will be in the matrix element, not in the voltages and all that. Okay, so I want to describe one more experiment, which is the Meissner, which is very similar to this, but profoundly different at the same time. And there, I think you can guess what's going to happen. So not Meissner, this is the Josephson Junction now. What's a Josephson Junction? When both are superconductors now, a superconductor and a superconductor. And that's really fascinating. So this was ever, and so let's look at the Josephson Junction now. Okay. And this is especially amazing to me because Brian Josephson predicted this experimentally before it was measured, and he predicted it as a grad student, and that was kind of pretty interesting, and primarily related to okay, so, and in fact it was so even John Bardeen, who was one of the leads in figuring out the microscopic theory of superconductivity, and also figured out a lot about semiconductors. As you know, he won 2 Nobel Prizes, one for semiconductors, one for superconductor. He even didn't quite believe that this can happen, though he had created almost the microscopic theory of superconductivity with Cooper and Schrieffer. But here's what happens in a Josephson junction. Actually, let me just use the picture. Here's the Josephson junction. Again, I mean, just two superconductors with a tunneling junction in between them now. Right? And conceptually, it's actually pretty trivial. You're like, instead of single particles tunneling across the junction, what about Cooper pairs tunneling across the junction now? Right? I mean, that's the basic idea. So, and the idea is this is one superconductor, and it's a macroscopic quantum object, meaning it has one wave function for all the Cooper pairs here. Right? Here's another superconductor. It has its own wave function. This is essentially like two atoms. And all the 10 to the power 20 whatever particles inside here are coherent with each other. They form one object, so they don't have any individual identity. Now, it is kind of rather difficult to believe that a macroscopic quantum object which physically is big or rigid like that, it can tunnel through the other junction without but when you actually measure this very carefully, what you'll observe is this is kind of the part which is kind of the G.I. Evers stuff, which is the tunneling gap part, right? But you also see a very interesting behavior. This is a DC. So there's a current which flows at 0 voltage, and this is to a certain level here. This is the DC Josephson effect. And what is even more interesting is what we'll see is the AC part of it. But let's talk a little bit about how what's the physical how it flows, the current flows. Yeah.
Junction and insulator.
Is the C region? Is an
Yeah,
this is an insulator. So it has a very large gap in all energies of interest here, meaning near the Fermi level of the two metals where the gaps will open. This material has no states at all. In that region. And the insulator can take many faces. It can be a physical insulator, it could be air, vacuum, something like that, but typically it's a physical solid state insulator like aluminum oxide or some wide band gap material typically. Yeah.
You said that the pairs in sections A and B are different?
A and B are different? Let's assume for now it's the same. They can be different. They can be two different superconductors as long as they're superconducting. But if it's a normal metal and superconductor, then we're back to J. Evers stuff, where you don't see this. Right? But if both are superconducting and you do the experiment carefully, you would see this. This is the Josephson effect. And these two can either be the same or different. We are talking about the same. If they are different, what you'll see is a little bit, you'll see actually two steps here because there are two deltas, two gaps, different gaps, and there's some other detail here. But let's assume they are the same for simplicity at this point. We'll not lose any physics by assuming that. But here's the crux of the matter now. So if you have the insulator, and then I take two superconductors, 1 and 2, and now I'm applying a voltage across it, just like J. Evers' experiment again, but now, and this is the insulator now. And actually, all right, so and we want to find out how does the current that will flow depend on the voltage here. And let me write it down first because it's actually a very interesting result. So when you do this experiment, what you will get is the current is some constant, which will come out later, times a sine function of 2 E over, I think, h bar times the voltage times time. I think, is that right? No, okay, just a sec. Yeah, this is correct. This is what you're going to get. So the current, if you apply a DC voltage, and this is very weird, you apply a DC voltage across it, a constant voltage, the current is oscillating with time. It's not constant. So a DC voltage is going to lead to an AC current. So it's an oscillator. The Josephson junction itself is an oscillator. And the frequency as a result, if you write it, and we'll just do a outline of a derivation, and then I'll leave it to you because I have told you that essentially once you write the wave function like this, this comes out in 2 or 3 steps. I'll outline the process, but you do it in your one of the assignment problems. Okay? So sine function and h bar is like 2 pi, right? And then you get 2e over h times V times T. That's your, I just broke it up in a little bit further. And you realize that this is the frequency, or mu, right, of oscillation, frequency nu of oscillation. And I mean, the fact that it is, what is most astonishing about this result is, well, first of all, it's already surprising that you might have an oscillating voltage, oscillating, DC output current for AC input voltage. This you can get in a traditional single particle physics if you have things like negative differential resistance and all that, where your di by dv is changing and it has instabilities. Here it is really because of the fact that the object here has one wave function, here has another wave function, but the phases are out of phase, and we'll see that that will play a very critical role in determining these oscillations here. But what is the most sort of amazing fact is this frequency of oscillation is extremely precise, very, very precise. It's one of the most precise. So what I mean, the frequency of oscillation nu, you can write it as omega, omega 2, which is omega is 2 pi times nu. I'm not going to try to, okay, so 2e over h times v, And why is it interesting? Now, going back to some of your discussions earlier, if I take a superconducting Josephson junction of one material, say lead, and the other is, say, mercury, or the other is aluminum, no matter what material you choose, the frequency is always going to be this. It's completely independent of what material you're choosing, first of all, right? It really does not depend on what material you're choosing, because it's 2e over h times voltage. And so if I take two exact same voltages and apply to any two Josephson junctions, so that would say that if my voltage is exactly the same, then there's no way this can change. The frequency has to be locked now to the voltage, right? And so what people have done in, say, at NIST, the Institute of Standards and Technology, is they have measured this down to precisions where they, so it's like a balance. You see, if you have one voltage which you don't know, and there's another which we know which is very precise, you can use it to calibrate voltages. So this is used today to calibrate voltages, because the change in frequency has been tracked to 10 to the power, I forget, minus 16 or 10 to the power minus 17. That's the precision, 16 digits precision. And typically this is a sign of something which is protected by topological features, and it's not. It's really independent of most of the internal details of the system. Yeah.
How does this compare to the line width of atomic transitions? If you're comparing this to how stable a frequency is for some sort of atomic clock, let's say.
Yeah. So how does it, for example, cesium atom line width decay? So I would say that this is the line width of atomic transitions is a measure for time, seconds, right? And then this is time is measured that way. Here actually is voltage, slightly different, but precision-wise, it's at this point of time is the most precise way of measuring a voltage. And so in a way, this is also related to transitions, because you have essentially like two atomic states here, and your it's continuously going between it's oscillating. The state is oscillating between the two as you drive with the voltage, and the speed at which that happens is driven by the voltage. So it's really a measure of the voltage. And today, 1 volt is defined as, I think there are, forget, 20,000 some of these in series, and it generates 1 volt. Basically, that's the experimental tool that's used to calibrate, or is your balance for voltage. Okay? I just wanted to kind of say that, and yeah, if there's another question.
It looks like no net current flows.
No. So if you integrate it over time, no net current flow. So it's going back and forth, right? But it's an oscillatory current. Yeah. And that's very important because, well, that's extremely important for many things as well, because if you apply DC, you're generating microwave signals. So by changing the voltage, you can go from, say, 10 gigahertz to very, very high frequencies. So you can generate power as well, as long as these are superconducting and low temperature. So. And here's the outline of, Joe, you have a question?
From this perspective, are these for fabrication is it not too difficult to fabricate if you don't, if this topologically protected, you don't necessarily, the
Yeah.
defects at the surface don't matter as much?
Yeah, so what will, the problem would be if you, so it is mostly independent, but as long as you are able to make the Cooper-Pairs tunnel, and that's, that part of it is the tricky part, meaning if this is too thick, or if the barrier is too high, or, there are some of these details, or if there are, shorts of normal metal through the insulator. So anything that messes that up has a possibility of messing, meaning the Josephson junction will still be going on, but it will be buried under some other signals. You can't extract it now. That's the issue typically. But so that's why you need to be reasonably clean. But after a certain level of cleanliness, it's fine. You can vary it, and it will still work. So that's what we mean by that. But more importantly, it really doesn't depend on which materials you choose. And that's very important here because the frequency doesn't depend. The current here will definitely depend. How much current is really. That depends on gap and tunneling probability and all that, but not the frequency. And that's really one of the major things about this. Yeah.
I guess another single particle tunneling, is it simple enough to say, let's say if the Cooper-Pair coherence length is 10 nanometers and your insulator is 11 nanometers, is that enough to stop tunneling? Or
yeah, so we haven't talked so much about the coherence length, but yes, so as long as the Cooper-Pair, the barrier thickness should be much smaller than the Cooper-Pair coherence length in order to be able to tunnel reasonable amounts of carriers across. Yeah, so okay, just I'll point out one more small thing here, that you can actually take this and make it into a slightly different architecture where you have two superconductors and they form a ring like this, right? Meaning two of these junctions, and they form a ring like this. And now this whole object here is one quantum object, and this is one quantum object. And now you can tunnel through. So this would be called a Squid Magnetometer, which is used to measure. Basically, what will happen is now inside here there will be an integer number of flux quanta that will be trapped inside here. It's two of them in parallel, and the magnetic flux lines kind of can move in and out through the insulator. But essentially, integer number will be trapped, and we go back to something like this here. I can explain why. When you measure something like this, you will see. So this is a very incredibly precise way of measuring a magnetic field. It's a magnetometer. It measures magnetic field with the precision of a flux quantum, for example. So this is and the current that will flow across here will have oscillations depending upon how many flux quanta you have inside, and that's okay. So I don't want to discuss that too much at this point. So I'll outline how we get this, and then move on to the next topic here. And this let's think of it this way. The superconductor 1 and superconductor 2 have two different wave functions. Square root of n1 times e to the power I theta 1. Okay, this is the macroscopic wave function. This one. And here you have square root of n2 times e to the power I theta 2. Right? And both n1 and n2 and theta 1 and theta 2, all four of them can change with time. Right, as they're variables of time. So we write down the Schrodinger equation. So thinking of this as one atom, as one big object, one atom, and we write down the Schrodinger equation for the left superconductor. It's IH bar d by dt of the wave function, the time dependent Schrodinger equation. That's n1 times e to the power I theta 1. Okay? That's d psi by dt. So IH bar d psi by dt is equal to the energy or Hamiltonian, of this object or its energy. So let's just write it as E1 for now, for argument's sake. Okay, times the. Right. Does that make sense? It's just the time-dependent Schrodinger equation, and we haven't done anything fancy at this point. So H psi, but we are saying it's H psi. It's in an eigenstate, so it's E psi. That's what we are saying at this point. But you know that this is not alone. It is coupled to the other atom or other object. How do you take that into account, right? And for that, what you must do is add to this some coefficient, which we'll do with matrix elements and other things like that, some coefficient times the wave function of the other. That's the linear combination of the wave function of the other, and the wave function of the other happens to be n2 times e to the power I theta 2. And this is a coupling coefficient between the two, or tunneling coefficient. It's a couple, there are two atoms or two objects, two quantum objects, and Schrödinger equation of the first is this is what couples the second to the first. And similarly, you will have an exact replica, but with all the signs, 1 and 2 is flipped, right? You get n2, the energy of the second state, E theta 2, is equal to the energy of state 2, theta 2 plus, again, here it should be A star, meaning the complex conjugate, but we can assume for simplicity at this point they're all, real, and we can do that. Right? So these are the two equations that when you solve them together, you will get this out. You'll get from these two equations. And the method to do that is basically you just go through the steps now. I think you, all right, so I'll just outline, well, I already have outlined, this is what you need to kind of solve. And here, the difference between the E1, okay, I don't want to kind of get into all the details at this point, but when you take the derivative, you will get d by dt of carrier density, d by dt of theta. There are two things here. So for example, this first equation will give you terms like, h bar by 2 times square root of n1 times n1 dot with d by dt, right? Times e to the power I theta 1. This is first term, plus there will be a, h bar times theta dot from this term times other stuff, and so on. So I don't want to kind of, you can work through this. You get two equations, and then what you can do at some point is realize that the, or define theta 2 minus theta 1, for example, as some angle delta. Okay? And what you will see is, or rather, this is what will come out from here, theta 2 minus theta 1, which is the rate of change of the angle or the phase of the two. The rate of change of the difference of the phase of two, not exactly the change, but just the difference, d over that, will become proportional to the voltage you apply between the two structures. That's what it's going to be. And you can kind of work through that. And then the current is going to be d of n1 or d of n2, whichever you choose, doesn't matter. Dn by dt is the number of particles. Remember, n is the number of particles that are carrying the current here, the Cooper pair, and current is rate of change of the particle density that's carrying the current, and that will give you what I wrote here. I am asking you to do this in the homework. It's few steps and you can get it. So upshot of this really is that as long as we think of the superconductor, all the carriers in the superconductor as one macroscopic object with one phase and one amplitude, I can explain much of the transport properties and flux quantization and Meissner and Josephson Junction, as well as the metal superconductor tunnel junction properties from here. Right? That's okay. So, all right. So I'll want to talk a little bit about the microscopic properties, and I'm realizing I'm again out of time now. But all right. So I'll leave this for you to solve. Okay. But I just wanted to say that this sort of precision in say the voltage definition of voltage, or is also seen. There are only two condensed matter or solid state phenomena where this sort of precision are seen. This is one, and the other is integer quantum Hall effect, where the precision is again like 1 in 10 to the power 10. Here it's 10 to the power 16. There it's 1 in 10 to the power 10 roughly. So these two are the, and both of them have some aspects of topology involved in them. Okay, so so the next topic. I realize I don't have as much time as I would desire to talk about the microscopic picture, but let me start the discussion, and we will finish it the next time then. By the way, any questions here? I think not. We'll move on. Well, this is not the best eraser here. All right, we'll leave it like that.
There's a rag over there.
Yep. Not terribly helpful either, yeah. What's that? Maybe the marker is the problem? Let's use mine. All right, so okay, so what I'll do is I'll talk a little bit about, again, I don't want to go into any depth into this topic, but why is it that Landau Ginzburg came up with this idea of a macroscopic wave function? And I will, so here's kind of the basic idea which kind of motivated what happened also a little bit later in the microscopic picture. That their argument was based on energy, energy of the whole system of a superconductor, for example, in a magnetic field or whatever be it. And my intention is not to go through any details, but just outline what was their thought process at this point. So the total free energy of object, which is a metal, is the free energy of the metal, meaning all the electrons in a single particle picture have kinetic energy, some potential energy, all of that together, certain energy there. But then all the superconducting properties are captured by all these other terms, which are related to the formation of this macroscopic wave function psi. There must be a driving force why a metal becomes a superconductor. It's a phase transition. That's their idea, Landau Ginzburg's idea. And it's actually a far-reaching idea because they also connected the phase transitions to symmetry breaking inside solids. Some more abstract but actually very important concepts. And what they found was symmetry breaking. The symmetry that's broken in a superconductor is the phase, or the gauge symmetry, if you might. So this is the phase of the wave function. If I take it around a loop, actually, gradient of this. Remember, we did an integral like that, right? If I don't close the loop, that's called the gauge. If I don't close the loop over a certain finite length, that's called the gauge factor, which is the angle difference of the phase as you go from one point to another. So that symmetry is actually broken, and when you minimize the total energy, so they had to write it in this way. The total energy must be proportional to the square of the wave function and the fourth power, and this is necessary because if you, and you have an alpha and a beta coefficients here. These are they just said that these are constants which I don't know anything about at this point. But if I can write it this way, these are the two factors here. You can identify this one very clearly as the kinetic energy, just p squared by 2m. Here's the, we wrote that out. I think I erased it just now. But, quantum mechanical momentum operator in the magnetic field becomes that, on psi, p squared by 2m. Here's, if inside my chunk of metal there is still a magnetic field, the energy is b squared by 2 mu. I think you know that from electrostatics. And you know that the Meissner effect is telling us that it is expelling the magnetic field. It's pushing it out. And that means there's a certain lowering of energy, and this factor must capture that lowering. So it's an interplay between the kinetic energy of Cooper pairs, magnetic field, and expulsion of magnetic field, and this must, explain this must be due to the expulsion of the magnetic field. That was their basic idea. Remember, all this stuff is happening. This everything that has psi in it, which is the macroscopic wave function, is a when you have a superconductor. If you don't have a superconductor in a normal metal, you just have the normal metal energy and the b squared by 2 mu, nothing fancy. But the fact that something goes from a normal metal here to a superconductor is as long as you have this situation. And what they also realized is these two coefficients, the coefficients of alpha and beta, or in other words, beta must be positive and alpha must change sign as you go from above Tc to below Tc. And then the total free energy was like this if alpha is greater than 0, and that's a normal metal. The moment you go below Tc, if this is negative, your function must become like this. And there is a minimum which is lower than the normal metal energy. And that's why the superconductor, the material would rather be here than here. and that energy difference is related to the gap of the superconductor. So that's the basic idea, and it's a phenomenological model, but it has a little quantum flavor to it. If you look at this equation, this is a modified Schrodinger's equation, p squared by 2m. This is kind of the energy, and there's a cubic term here. This is a nonlinear Schrodinger equation, and this is one of the great. Actually, one of the really very important findings that explain the existence, why should it actually go into this phase transition in the first place. It is not telling you any details of how is it happening microscopically, but just from the constitutive equations, what they're saying is, so it can explain all the hallmarks we talked about, Meissner effect and all that sort of thing, but it's not going to tell you what is the gap. It's not going to tell you some of the other details. Yep.
So I forgot his name, but whatever his name, he proposed that the transition to a superconducting phase is just like it is just a phase transition.
It is a phase transition, yeah.
And that's governed by some free energy equation.
That's correct.
Can you relate that to a thermodynamic?
This is a thermodynamic phase transition. Okay. It is indeed, yeah. And there are conjugate variables, just like any other thermodynamic phase transition. We have pressure, volume. Here, what you get is it's actually the number of particles and the phase of the particle, theta. So the conjugate variables here are n and theta, and they behave as delta. And so there's that aspect to it. So there. Okay, so it is very similar to many of the thermodynamic phase transitions, okay. and if you're interested, I would suggest reading up a little more. My intention was just to point you in that direction and then move on to the next topic. And I could spend some time, but I would rather, I'm kind of also somewhat interested in covering the next topic, which is the one of the ways that it can actually do this physically. Why would it do that, right? The energy cost we understand, but microscopically, what is the driving force, right? What is the driving force for it to be able to form a condensate like that and such things? And that's what we wanted to talk about, and that really depends on the Froelich. So the hints for that came from experiments, but before that, here's the experiment, one of the most critical experiments. So if you measure the critical temperature of a superconductor as a function of the mass of the atom from which you made the superconductor, the mass of the atom. Here, all of these are mercury, but there are different isotopes of mercury. What does that mean? It means that their masses are different because they have different number of neutrons in them. Neutrons are not participating ordinarily in electrical transport, right? But they are having a big effect on the TC of the material. Big as in, reasonably, very clear effect, a very clear tendency that a heavier mass has a smaller TC. And if you plot it carefully, what you will see is that the critical temperature goes as 1 over square root of the mass of the atom. We're not talking about the effective mass of electrons, this is the mass of the whole atom. You can pretty much forget about all the electrons, it's all the sum of proton and neutron masses, right? So, and that, immediately the sign was that it is related to phonons. Because phonon frequencies, phonon vibrations, we know are related to the mass of the atom, right, or the vibration of the atom. And spring constants, we have talked about, if I have two masses, M1, if I have M and K, we know that the frequency is square root of K by M, right? And this sign immediately gave a hint that it is related to phonons. And in fact, this experiment was kind of also motivated by a theory of Froelich, which is the Froelich interaction. We have talked about electron-phonon interaction in semiconductors. It's exactly the same picture here, except here it's a many-particle interaction. There are 2 electrons and 1 phonon involved. So, and we'll leave this to the next class, but what we'll see is the idea by which the gap is formed, the whole system can lower its energy, is all related to this picture that an electron is moving along and it will emit a phonon, and that will be absorbed by another electron, right? And there's exchange of phonons between electrons. And this has got to do with lattice distortions. And as the electron goes through, it distorts the lattice around it. But the distortion of the lattice is very slow compared to the speed of the electron. So electron is far gone, it's about 100 nanometers away, and the distortion now captures another electron, and the two are coupled, you know. So we are going to see that in the next class, and the hint for that came from isotope effect, and from there we'll be able to derive an expression for the gap of the superconductor, you know, and that's also kind of interesting. We'll do that in the next class then. Okay, good. Let's stop for today.